Researchers have made significant progress in applying machine learning to physical sciences, such as molecular dynamics and coarse graining, by combining state-of-the-art approaches with a deep understanding of physical problems. This has led to a push towards integrating machine learning with classical numerical methods to improve problem-solving in the physical sciences. The authors argue that insights from classical approaches can enhance machine learning algorithms, not only for specific problem classes but also for machine learning in general. Inspired by recent theoretical advances in algorithmic alignment between graph neural networks and dynamic programming, the authors extend this analysis to classical PDE solvers, incorporating physical considerations. They present an overview of simulation approaches that have yet to be incorporated into state-of-the-art machine learning methods, but hold potential to make machine learning approaches more accurate and efficient. The development of graph-based learned solvers is compared to the development of smooth particle hydrodynamics from molecular dynamics in the physical sciences. Figure 1 illustrates the physical scales on which these methods operate, placing graph network-based approaches, mesh graph nets, and graph network-based simulators in relation to their classical counterparts. By analyzing the development trajectory of classical numerical methods, the authors aim to inform new ideas for algorithms, contributing to the goal of learning from the physical sciences. This comparative analysis provides valuable insights into the potential of integrating machine learning with classical numerical methods to improve problem-solving in the physical sciences. This section explores the relationship between graph neural networks, GNNs, and classical numerical methods in simulating physical systems. It focuses on two mature learned solvers, graph network-based simulators, GNS, and mesh graph nets, comparing them to three classical methods: molecular dynamics, MD, finite point set method, FPM, and smooth particle hydrodynamics, SPH. Graph network-based simulators, GNS, utilize an encoder-processor-decoder framework to approximate the dynamics of a particle system. The differential operator D is learned through this structure, which takes in 1 to 10 previous states, encodes them into a graph, applies a multi-layer graph network, and then decodes the result back to physical space. The loss function is computed as the mean squared error between the learned and target accelerations. While GNS shows promising results for fluid simulations and fluid-solid interactions, it struggles with deforming meshes like thin shells. Mesh graph nets, on the other hand, introduce an additional set of edges to define a mesh, allowing for better representation of complex interactions. By splitting the interaction function into simpler components, it closely relates to the superposition principle in physics. This approach also includes adaptive remeshing to model a wider range of dynamics, preventing the loss of high-frequency information due to mesh deformation. Furthermore, mesh graph nets extend the output vector y to predict additional targets such as stress fields, and the input includes a predefined mesh. In summary, this section delves into the connections between GNNs and classical numerical methods, highlighting the advancements and limitations of GNS and mesh graph nets in simulating physical systems. The research paper delves into the connections between graph neural networks, GNNs, for simulating physical systems and classical numerical methods. It begins by outlining the mesh graph net scheme, which consists of an encoder, processor, and decoder. This scheme is designed to simulate complex physical phenomena using GNNs, focusing on the decomposition of the algorithm into its constituent parts. The paper then explores similarities between the development trajectories of particle-based methods and GNN-based approaches to simulations. In particular, it highlights the connection between molecular dynamics, a widely used simulation method that generates trajectories of an n-body atomic system, and mesh graph nets. Both approaches construct connections or edges based on spatial distances up to a fixed threshold, compute interactions based on these connections, and use iterative updates or repeated application of graph network layers to extend the effective interaction radius beyond immediate neighbors. They also share translational invariance with respect to accelerations and permutation equivariance with respect to particles, utilizing a symplectic time integrator. However, the main difference lies in the computation of accelerations, where molecular dynamics evaluates the derivative of a predefined potential function, whereas mesh graph nets employ a learned model. The paper further discusses the similarities between smooth particle hydrodynamics, another particle-based method originating from astrophysics, and GNN-based simulators. Both obey the continuum assumption and are constrained to extremely short time intervals, unlike molecular dynamics which presumes a discrete particle distribution. However, while molecular dynamics and smooth particle hydrodynamics explicitly encode geometric relations and physical laws, GNN-based methods require learning these parameters and relations from data. A key advancement of mesh graph nets is the explicit superimposition of solutions on both sets of edges, outperforming the implicit distinction of interactions in conventional methods. This approach can be applied to all conventional particle and mesh-based simulations in engineering. By borrowing the fluid particle model from fluid mechanics, the paper connects mesh graph nets to classical methods and GNN-based simulations under the fluid particle paradigm. The fluid particle model, situated on an intermediate scale between microscopic molecular dynamics and macroscopic smooth particle hydrodynamics, views particles from the perspective of a Voronoi tessellation of the molecular fluid. This pseudo-particle construction is closely related to the mesh graph nets construction, where each mesh node corresponds to an ensemble of atoms in thermal equilibrium. The paper concludes by highlighting the potential for GNNs to bridge the gap between classical numerical methods and learned approaches, leveraging the fluid particle model to understand and simulate complex physical phenomena. In the context of simulating physical systems, graph neural networks exhibit parallels with classical numerical methods. This is particularly evident in smooth particle hydrodynamics and dissipative particle dynamics, which operate on pseudoparticles and necessitate a sufficient number of atoms per pseudoparticle to be considered a thermodynamic system. The injection of Gaussian noise in graph-based simulators can be likened to forcing the learned model to predict the true output despite noisy inputs, leading to convergence to the central limit of the estimated conditional distribution of the acceleration. The construction of Voronoi tessellations, which governs that the size of the cells is inversely proportional to variations in their properties, is also discussed. This concept is used in mesh refinement algorithms, such as mesh graph nets, where more sampling occurs in regions with high property variation. The relationship between graph neural networks and numerical schemes is explored, highlighting the diversity of numerical approximations of partial differential equations, PDEs, depending on the peculiarities of the PDE of interest. Various numerical methods are discussed, including finite difference methods, finite volume methods, finite element methods, smooth particle hydrodynamics, and dissipative particle dynamics. Comparisons are made between concepts from classical methods and state-of-the-art learned algorithms, focusing on data augmentation with white noise and data augmentation by multi-step loss. Noise injection is seen as an effective regularization technique, allowing for longer trajectories during training, but the issue of tuning the noise scale manually is noted. The connection between noise injection and mesoscopic particle methods is explored, which could aid in understanding the influence of training noise. Multi-step loss, which involves training a model to correct its own mistakes via a short trajectory generated during training, is also discussed. The varying results of this approach are highlighted and compared to adaptive time integrators used in ODE routines, which guarantee long-term rollout stability. Graph neural networks, GNNs, have emerged as a promising tool for simulating physical systems, offering an alternative to classical numerical methods. One key technique in this domain is the use of adaptive step sizes, which correct for future deviations in trajectories without altering the step size, a concept popularized in neural ODEs. Equivariance bias, a property essential in physics due to energy conservation, has seen significant advancements in recent research. Incorporating equivariant features into GNNs has been shown to boost performance, as demonstrated by Brandstetter et al. 2021, Schutt et al. 2021, Batzner et al. 2022, and Musalian et al. 2022a. Another technique used in GNN training is inputting multiple past steps, which helps prevent overfitting and improves performance, as observed in Sanchez-Gonzalez et al. 2020, Pfaff et al. 2021, and Brandstetter et al. 2022. However, this approach raises questions about physical justification, potentially assuming non-physical non-Markovian retardation processes. GNNs are well suited for spatial multiscale modeling tasks, such as coarse graining, particularly in molecular dynamics and engineering applications. They can operate on irregularly spaced data, a crucial capability for most coarse graining approaches. The locality of interactions is another important aspect, with GNNs defining edges based on an interaction radius and expanding the receptive field of each node with additional layers. However, Muselian et al. 2022a challenge the assumption that a large receptive field is responsible for the success of learned simulators, suggesting that equivariant graph networks with fixed interaction neighbors can perform equally well. The flexibility of GNN-based simulation approaches is further demonstrated by their ability to seamlessly combine particles and meshes, as shown by the Mesh Graph Nets framework, Pfaff et al. 2021. This capability to transition between particles and meshes is a key strength of learned methods, offering a promising avenue for future research. Machine learning in physical sciences has underutilized concepts, particularly graph neural networks, GNNs, which are closely related to classical numerical methods. Coarse graining is a key concept that simplifies a system while preserving its essential properties. This process involves Voronoi tessellation, similar to the fluid particle model, assuming each mesh cell is small enough to be treated as being in equilibrium. Stencils, commonly used in regular grid simulations, can be adapted with GNNs. Two notable works are mentioned. One inspired by the weighted essentially non-oscillatory scheme, WENO, and another based on the finite volume method, considering fluxes at cell boundaries. Another approach, inspired by the finite element method, introduces finite element networks that weight contributions from neighboring cells by their volume. Integration schemes are also crucial, with higher-order integrators providing robustness. Symplectic integrators, although less clear in learned Hamiltonian neural networks compared to conventional molecular dynamics integrators, could potentially enhance the accuracy and realism of GNN-based simulations. Untapped ideas from classical approaches include adding noise during inference to simulate Brownian motion, using multiple time steps, and feature engineering inspired by the volume of fluid method, discrete element method, and shock-cap Turing methods. These concepts could potentially enhance the accuracy and realism of GNN-based simulations in the physical sciences. The relationship between graph neural networks for simulating physical systems and classical numerical methods is a crucial area of exploration. By incorporating insights from classical solvers, the development of learned solvers can be accelerated, leading to improvements in performance, explainability, and data efficiency. Examples of learned solvers that have already integrated elements from classical solvers include particle-based methods such as molecular dynamics, smoothed particle hydrodynamics, and the fluid particle model. Future directions for integrating classical numerical methods into learned solvers are also explored. Combining the best of both particle and grid worlds, similar to the particle in cell method and its successor material point method, could enhance simulation speed and accuracy. Techniques like the fast Fourier transform and wavelet transform, as seen in the Fourier neural operator and PDE-net, could offer a rich set of tools for multiscale modeling. Studying classical PDE solvers and their past development is essential to guide the creation of learned PDE solvers. Combining learned integrators with adaptive integration schemes, akin to the current Friedrichs-Louis (CFL) condition for classical numerical methods, could help bound the time step and allow for exploring smaller time steps than the critical value. This integration could potentially lead to more accurate and efficient simulations. In conclusion, integrating classical numerical methods into learned solvers holds significant potential benefits. Understanding and leveraging past developments in classical PDE solvers is crucial for accelerating the development of learned solvers, which can ultimately result in more powerful tools for simulating complex physical systems. This research paper delves into the connections between graph neural networks and traditional numerical methods for simulating physical systems. It commences by acknowledging Kundal and Strack's discrete numerical model for granular assemblies, a foundational work in understanding complex systems behavior. The authors then reference Dormand and Prince's family of embedded Runge-Kutta formulas, a numerical method used to solve ordinary differential equations. They also explore Espagnolo's fluid particle model, instrumental in simulating fluid dynamics. The paper highlights Frey et al.'s neural scaling approach for deep chemical models and Hahn et al.'s PDE-NET, a deep learning model capable of learning partial differential equations from data. Additionally, it mentions the volume of fluid (VOF) method developed by Hurt and Nichols, a technique used to simulate free boundaries in fluid mechanics. It touches upon the smooth particle hydrodynamics method, first proposed by Gingold and Monahan, commonly used in astrophysics and fluid dynamics. The authors discuss the dissipative particle dynamics model developed by Hugerbrug and Coleman, combining molecular dynamics and smooth particle hydrodynamics elements. They also reference Lino et al.'s multiscale graph neural networks for simulating continuum mechanics and Musalian et al.'s learning local equivariant representations for large-scale atomistic dynamics. Furthermore, the paper highlights Pfaff et al.'s demonstration of how graph networks can be used to learn mesh-based simulation. It also cites Pradesha et al.'s application of finite volume neural networks to model subsurface contaminant transport. Lastly, the paper concludes with a reference to Roklin's rapid solution of integral equations of classical potential theory, emphasizing the importance of classical numerical methods in understanding physical systems. The intersection of graph neural networks and classical numerical methods for simulating physical systems has been extensively explored in various studies, including fluid simulation, molecular conformation prediction, and physics-informed deep learning for turbulent flow prediction. Understanding the connections between these two approaches is crucial, as they can complement each other in different contexts. Graph neural networks can approximate solutions of partial differential equations, fundamental in many physical systems, and leverage spatially varying coefficients in their simulations. Rotationally equivariant features in 3D data processing are also essential, as demonstrated by novel models like ReMuse-GNN, designed to simulate continuum dynamics. Furthermore, neural execution of graph algorithms has potential applications in optimizing computational efficiency and accuracy. In molecular simulations, generative coarse graining of molecular conformations is significant, as it could enhance our understanding of complex molecular interactions and properties. The development of neural networks capable of reasoning about abstract concepts paves the way for more sophisticated AI models in the future. The integration of graph neural networks with classical numerical methods is an area of ongoing research, with potential breakthroughs in fields like fluid mechanics and molecular biology, and opportunities for interdisciplinary collaboration and innovation.